So in this section we will discuss the projection of a vector onto another vector. So let me draw it and show you what I mean. So let's say this is my vector v, and let's say this is my vector u. So the projection of vector u onto v is, let me drop a perpendicular from the tip of vector u to vector v. Okay, so the projection of vector u onto v is this vector p, right, which is a scalar multiple of the vector v itself. Okay, and if this is p and this is u, then this vector becomes u minus p, right? And u minus p is perpendicular to the vector v. So now it's easy to find out what vector p is, because if u minus p is perpendicular to the vector v, then u minus p dot v has to be equal to 0, which would imply that u dot v is equal to p dot v, which would imply that u dot v is equal to c times v dot v, because p is equal to cv, right? Which would imply c is equal to u dot v by v dot v, right? And hence p is equal to cv is going to be equal to u dot v by v dot v times vector v. So let's take an example here to make things more clear. So let's say I've got two vectors u and v, and u is given by, let's say, 1 2 5, and the vector v is given by, let's say, -1 0 2. All right, so we need to find the projection of vector u onto vector v, and we can do that by first of all calculating what is u dot v by v dot v. And let's calculate that. So I think that will be -1 plus 10 divided by 1 plus 4. So this will be 9 by 4. So the projection of vector u onto vector v will be equal to 9 by 4v, and that will be equal to -9 by 4 0 9 by 2. All right, so one of the related class of problems is finding the distance of a point from a line. So let's say we wanted to find this distance of the point, let's say point 1 1 1, from the line which is given by the equation x y z is equal to, let's say, 1 to 1 plus t times let's say -1 1 1. All right, and also say we want to find the point which is on the line and is closest to p. So let's try to solve this problem. So to begin with, first of all, let me draw the line. So let's say this is my line L, and let's say q be any point on the line, any point on the line. So in this equation of line, if I put t equal to 0, I'll get that 1 2 1 is a point on the line. So let me call that point q. So 1 2 1 is a point on the line. Okay, and let me draw the point p also. So let's say p is over here and p is 1 1 1. Okay, so the vector qp, so this will be vector, oh god, assume that point p is over here not here. So the vector qp can be drawn like so, right? And this is line L, and if I try to find the projection of vector qp on line L, I need to draw perpendicular, right, from point P to line L, right? and this guy will, let's call this vector p. This vector p will be my projection, and this vector will be vector qp minus p, right? And the distance of the point p from this line is going to be the length of this vector, right? So let's start by calculating what vector qp is and what vector p is first of all. So let's find what vector qp is. So the vector qp will be 1, so it will be 1 minus 1, and then the second element will be 1 minus 2, and the third element will be 1 minus 1 again. So this will be equal to 0 minus 1 0. All right, and this guy, this vector p, is the projection of vector qp on the line whose direction d. So line L has a direction vector d, which is given by this guy, right? So d is equal to minus 1 1 1. Okay, so we need to find the projection of qp on this line whose direction vector is given like so. So we know we have done this already many times, so we know how this can be done, right? So the vector p here would be given by the dot product of qp with d divided by dot product of d with itself and multiply that with d. All right, so you can actually solve it out yourself. I think I'm going to write down the exact solution here. So this turns out to be minus 1 by 3 times minus 1 1 1. Okay, so we have got qp, we have got p. So let's try to find out what is qp minus p. So qp minus p is going to be 0 0 minus 1 0 minus, and this becomes plus. So plus 1 by 3 minus 1 1 1. All right, and this finally becomes minus 1 by 3 minus 2 by 3 and 1 by 3. So the distance of point P from line L is the length of this vector, and we already have this vector qp minus p. So the length of vector qp minus p will be equal to 1 by 3 times root of 1 plus 4 plus 1, and that will be equal to root 6 by 3. So there you go. And I think there was one more part to this, right? And also we wanted to find out the point on the line L that is closest to the point P. So let this point be A, all right, which is denoted by x, y, z. So then we know that the vector QA is actually equal to the vector P. So let me calculate what vector QA is. So the vector QA is going to be equal to x minus, it's 1 to 1, right? So x minus 1, y minus 2, and z minus 1. And this is equal to vector P, right? And vector P is this guy. So this is equal to 1 by 3 and then minus 1 by 3 and minus 1 by 3. All right. So which basically means that x is equal to 1 plus 1 by 3, right, which is equal to 4 by 3, and y is equal to 2 minus 1 by 3, which is equal to 5 by 3, and z is equal to 1 minus 1 by 3, which is equal to 2 by 3. So the point that is closest to, so the point on the line that is closest to the point 1 1 1 is this point. Okay, so now that we have learned how to find the closest distance, so the closest point to a closest point on a line to another point, let's try to tackle another class of problem. So let's try to find the distance of the plane. Let's try to find a distance of the plane x minus 2y plus z is equal to 0 from the point P, which is, let's say, given by 0 1 1. Okay, so let me draw it out to make things more clear. So let's say this is my plane. Okay, and let's say I have a point P here, and P is given by 0 1 1. So what I want to do is to find the distance between point P and this plane. Okay, so to do that, let me consider Q be any point on the plane, right? And it seems that 0 0 0 is definitely on the plane. So let me take point Q, which is 0 0 0, and it lies on the plane. Okay, then the required distance that I'm talking about, that we are looking for, that is the distance of point P from the plane. So this required distance is nothing but the projection of vector PQ. Okay, is the projection of vector PQ onto the normal to the plane. So let's say this is a normal vector to the plane. Okay, let it be n. So the distance that we are looking for is nothing but the projection of this vector PQ onto the normal vector of the plane, right? And again, so the problem is quite simplified now, right? So we need to calculate what, the vector PQ is. So the vector PQ will be equal to 0 and then 0 minus 1 and then 0 minus 1. So this will be 0 minus 1 minus 1, and the normal vector to the plane would be 1 minus 2 1, right? It's evident from the equation here. So it will be 1 minus 2 and 1 minus 2 and plus 1. Okay, so the projection PQ on n, and let us call it P, right? So the projection of PQ on the normal vector n, and let's call it P, right? It's going to be given by vector PQ dot n divided by n dot n times the normal vector n, right? And you can actually work out the math here. So it's going to be 1 by 6 times n, and n is 1 minus 2 1, right? So finally, the distance of point P from the plane is the length of this vector, and this will be equal to 1 by 6 times square root of 1 plus 4 plus 1. So it will be nothing but root 6 by 6.